Hello, and welcome to Summarize Science. Have you ever seen a robot navigate a room and wondered how it builds a map while also knowing where it is? This process is called SLAM, for simultaneous localization and mapping, and it's crucial for things like self-driving cars and augmented reality. Traditionally, getting accurate, real-world scale maps requires special cameras with depth sensors, which can be expensive and complex. But this paper, called Dropping the D, RGB-D SLAM without the depth sensor, introduces a new system that achieves the same high-quality results using just a single, normal RGB camera. So how does their system, named Drop-D SLAM, pull this off? It's a clever pipeline that uses 3 pre-trained AI modules working in parallel on each video frame. First, a metric depth estimator analyzes the image and creates a dense map of how far away everything is, essentially guessing the depth. At the same time, a learned keypoint detector finds stable, unique features in the scene, which act like landmarks. And third, an instance segmentation network identifies objects that are likely to move, such as people. The system then creates a dynamic mask to block out the moving objects, ensuring they don't confuse the mapping process. The static key points are then combined with their estimated depth values, creating a set of 3D points. This set of 3D features is then fed into a standard, unmodified SLAM backend, which does the heavy lifting of tracking the camera's pose and building the map. The results in static, non-moving environments are already very impressive. Looking at this table, their method achieves a mean error of just 7.4 centimeters, which is highly competitive with modern, fully learned approaches. Interestingly, it even outperforms the researchers' own baseline that used a real depth sensor from the dataset. This is because learned depth models can sometimes produce more coherent and dense depth maps than real structured light sensors, which struggle with reflective or textureless surfaces. But the performance in dynamic environments, with people walking around, is where this system truly shines. Here, Drop-D SLAM achieves an incredible 1.8 centimeter average error, outperforming all prior methods, including specialized systems designed specifically to handle dynamic content. It does this without any complex motion modeling, simply by being extremely effective at identifying and ignoring features on moving people. This demonstrates that a robust filtering strategy can be more effective than trying to explicitly model the complex movement of objects in a scene. Just how important is that dynamic filtering? This ablation table shows that if you turn off the instance masks that identify people, the error skyrockets from 1.35 centimeters to 27 centimeters, causing the system to fail. This single component is absolutely essential for its success in real-world environments. The table also confirms that using modern AI-based keypoint detectors provides a noticeable, though smaller, boost in accuracy over traditional methods. So let's recap the key breakthroughs here. The Drop-D SLAM system successfully replaces an active depth sensor with a combination of off-the-shelf AI modules. It achieves state-of-the-art accuracy, especially in challenging dynamic scenes, by aggressively filtering out moving objects rather than trying to model them. And it does all of this in real time, running at 22 frames per second on a single GPU. What this means for the future is that powerful 3D mapping and tracking capabilities could become much cheaper and more widespread. We could see more affordable and capable home robots, drones, and AR glasses that can understand and interact with their environment using only a simple camera.